All right, thank you for coming to our space-time seminar. They have Connor O'Brien here, so yep.
This is Connor O'Brien. He is a fifth-year PhD student, PhD candidate, I should say, the more important, at Boston University, and he is under his advisor Brian Walsh, doing space weather modeling using machine learning, and we're going to hear about a specific instance of space weather modeling and machine learning right here at talk. So go ahead, Connor.
Excellent, thank you very much, Ramon. Yeah, so that was a great introduction, but so yeah, I am the one here talking to you today, but there's obviously a whole bunch of wonderful collaborators, including Yingzhou and Raviz, Samira, and Huaming, with whom I've learned all of this machine learning stuff. I've never taken a class, I just, drank from the fire hose that those individuals provided. So that's where this expertise comes from. So to talk a little bit about the problem that we're trying to solve, or the domain that we're talking about, so we can all get oriented. If you have some physical phenomenon at Earth, some physics that you want to investigate that you suspect is being driven by the solar wind, and this is a reductive way of describing many of our life's work. Many individuals in this room, their whole life's work can be summed up by that. You need to have this, you tend to correlate your physics at Earth with some solar wind condition that you're saying is impacting the Earth at that time. Ideally, you'd want to have a spacecraft parked right here, right ahead of the nose of the bow shock all the time, right? Because that's the solar wind that's about to strike the Earth, or the Earth's magnetosphere, rather. Unfortunately, due to orbital constraints, we don't have a spacecraft just parked there venting fuel all the time. But where you can park a spacecraft is at the first Earth-Sun Lagrange point. And that's where, we've studied some amount of orbital mechanics in this room, presumably, but that's, where the Earth and the Sun equally pull on things at that point. It's sort of the reductive way of talking about it. The L1 point is 1.5 million kilometers upstream of the Earth. It's roughly 230 Earth radii. And while that is only 1% of the way to the sun, it's still a good distance away from the Earth. So what's happening at the L1 point is not necessarily what's happening at the nose of the bow shock. So if you want to use data from some of the myriad of space weather monitors that we have at the L1 point, if you want to use that data for your correlation study at Earth, or say you have an event that you want to determine what the solar wind was doing at that time, you're going to have to propagate the conditions that those space weather monitors are measuring to the nose of the bow shock using some sort of algorithm. Now, we've had spacecraft at the L1 point for many decades. So many people have had, many very smart people have tried to solve this problem in various ways. And one of the earliest ways of doing that is called ballistic propagation, which I'll introduce here in a second. But you have a velocity and a distance. You measure a plasma flow velocity at L1, and you know the distance to the bow shock nose roughly. So just divide that distance by the velocity and do a little time shift by the resulting time, right? So this is one of the earliest techniques of shifting this data around. And right here we have basically timing errors associated with this method for 3 different quantities that you might want to care about. So these errors are determined by doing this simple ballistic propagation between IC3 at the L1 point, and then comparing that data to IMP8, which is a spacecraft goes into the Earth. Then after that ballistic propagation, that simple delay time is calculated, then the data from the 2 spacecraft are lined up to achieve sort of like maximum correlation. And then that's taken to be the true time of propagation between L1 and the Earth. As you can see, those 2 numbers are often, most often, not different at all, right? All of these histograms peak at 0. But what you can see is that there are these broad wings. You can get this timing wrong by up to an hour in both directions, which is not ideal if you're trying to study some, say do a statistical analysis, a long time scale statistical analysis, things that are. So one way that this method can be improved, and this is what is frequently done nowadays, is using a technique called combining two techniques, minimum variance analysis and planar propagation. Basically, you assume that you start with a physical assumption. The physical assumption is that structures in the solar wind flow are much, much larger than the system that you care about. They're very, very large. As such, you can consider them to be a series of infinite planes in which all of the quantities that you care about, your densities, your velocities, your magnetic fields, are constant, or rather the same within those planes. Frequently, they're called phase fronts. You can determine, if you start with this assumption, you can determine the orientation of these phase planes using minimum variance analysis, where you choose a time interval, roughly, you roughly choose a time interval and you find the direction in which all of these quantities are varying the least, hence minimum variance. And you assume that to be the normal to the plane. You then have a plane with an orientation and a velocity. So you measure this at a spacecraft at L1. You have some target point, the nose of the bow shock. You simply advance the plane at that velocity until it strikes the point that you care about, right? This is nice, you know, it bears some similarity to ballistic propagation, but it's not quite. It has a little bit more physics going on in it, but it's not without its limitations. So one of the primary limitations of this method is called the out of sequence arrival problem, where essentially if you have this spacecraft at L1, you can have the situation in which you measure a plane with a particular orientation at one time, and then later you measure another plane with a particular orientation that might be more highly inclined, maybe faster, but either way, whatever may be, it can happen that plane 2 is predicted to arrive before plane 1 at whatever point you're propagating to. Essentially what this means is that plane 2 has overtaken plane 1, passed through it unmodified. We know that this isn't physical. You know, if a sort of fast solar wind flow runs into a solar wind flow, it forms a shock. That's a co-rotating interaction region, right? Or various number of other things that it could be, but both of these would be modified in some way by this interaction. This is one limitation of this method, and you might be wondering, like, how often does this happen? I don't have a strict number for you, but it could be happening quite frequently. And that's because we know that the solar wind flow isn't a series of infinite planes. The solar wind flow has all sorts of wonderful things going on in it, all sorts of wonderful structure. Here we have one visualization of this structure. Essentially, you can consider the solar wind a series of, you know, interconnected, bundled up spaghetti of flux tubes. Plotted here are the current sheet boundaries between these flux tubes, so essentially slices. So on the left is a slice from the sun's eye view, so face on with a cross section of the bow shock and magnetosphere plotted for scale here. And then on the right, you have a side-on diagram with the L1 point and the size of the system here. And what you can see is that these flux tubes are on the scale size of the system itself, you know, 50 to 70 Earth radii around. So at the L1 point, if you imagine, so this whole pattern is moving to the right with the solar wind flow velocity. You could imagine that whatever parcel here passes over the L1 point is not necessarily what's going to be hitting the magnetosphere. This is a situation that the physical assumptions that go into the minimum variance planar propagation combo algorithm can't capture. And indeed, this can, yeah.
Is there a specific reason why the solar wind would be structured in those kind of like bundle of flux flow? Like, is there like, do we have like physical reasons to think that, or is it like a thought experiment?
This is something that's, so there is there, so one could imagine that it's the flow coming out of various spicules, things of that nature.
Okay.
This physical model has been proposed to account for some observations that we notice, you know, electron straw running in different directions.
So like, but the size of the bundles are somewhat the one we could deduce from observation?
Yes, yes,
Okay.
that size that I quoted is deduced from observation.
Oh,
yes.
okay.
There are people who would argue with this, maybe people in this room might argue with me on this, but either way, we can all agree that the solar wind flow is not a series of infinite planes, and in fact has a lot of interesting processing going on within it. What we can also see is spacecraft at the L1 point are frequently in you can see spacecraft being in these different parcels of magnetic field and plasma. So on the top is measurements from the ACE spacecraft, which is one of our solar wind monitors. On the bottom is data from the WIND spacecraft. This is vector magnetic field. And what you can see is for the period of roughly an hour here, ACE is measuring steadily southward BZ, this red line is negative. And WIND is measuring steadily northward BZ. We know that BZ is one of the orientation of BZ is a strong indicator of how much energy is being transferred into the magnetosphere. You know, strongly southward BZ transfers a lot of energy. Depending on which spacecraft you, based on your algorithm, is propagated to the nose of the bow shock, depending on which spacecraft you believe, radically different things are going to be happening in the magnetosphere. So this was a problem that comes up with some regularity. The reason why I've dug into this one algorithm so much is that this algorithm is what is used to construct the Omni database. So many of us in this room have heard of Omni. It's a database of solar wind conditions measured at the L1 point with all of our monitors, a constellation of monitors. So right now that's ACE, WIND, and Discover, but there are others in the Omni database if you go back further. Propagated to the nose of the bow shock using this algorithm that I just outlined for you, or a particular implementation of it. That means that this database has sort of, to my mind, three main limitations. So one of those limitations is this out of sequence arrival problem that I talked about. Another limitation kind of buried in that is that it ignores processing from L1 to the bow shock and these boundaries between flow parcels. So by using this planar propagation assumption, we're ignoring some physics. And also we have no physically meaningful uncertainties attached to these values that Omni is predicting. It's just a time shift. So even though, as we've determined, as I've shown, determining that time shift is a difficult and uncertain process. But all that we have are the instrument uncertainties, which by this point have been far exceeded by the timing uncertainties of the propagation itself. As such, a lot of us use Omni. So in 2021, out of all of the papers that were published in space weather and space physics, 42% of them almost half used data from the Omni database. So this
and how much of that other half is papers that are discussing topics that don't care about what's going on in the solar wind?
So the way that this was determined is this was from the Omni team and they just scanned for the citation. So it could very well be that those 57.9% are discussing this problem and maybe even using Omni data and just forgetting to cite the Omni database. So or they're talking about something that's not affected by this. Precisely. So this is of central importance to, even if you don't study the solar wind, certainly we all in some way care about the way that the solar wind impacts the magnetosphere. So we propose to address these limitations through sort of a novel machine learning method, basically a Bayesian recurrent neural network. In order to develop this model, we basically need three main ingredients. So we want to train this algorithm to reproduce one data set from another. We want to train it to reproduce a near-Earth spacecraft's data from data taken by spacecraft at the L1 point. So here we choose MMS1 as our target near the Earth, and WIND as our solar wind monitor L1. And the third ingredient is a sufficiently representative network architecture, which I'll show you. But first, talking about the data. Training neural networks, machine learning broadly, comes under the umbrella of big data. So we need a big data set. In order to assemble a big data set of MMS1 targets, we relied on an automatic classification algorithm that essentially looks at the 3D ion distribution off of FPI, which is the fast plasma investigation on board MMS, and splits the distribution functions that this instrument takes into 4 categories shown here, or examples of which are shown here. In the top left, the solar wind, you can see, so this is a polar plot. You can see that the solar wind looks as expected. It's a highly concentrated beam in one direction. You can also look at foreshock, which is a beam in one direction, and then you can see around the outside of the polar plot the counter streaming ions there. The magnetosheath looks a lot like the solar wind except thermally broadened. And then the magnetosphere is this isotropic high energy distribution that we expect. So this classifier allows us to automatically partition all MMS data from 2015 through 2022 into these 4 categories. There's a couple more sort of stipulations in there, but I won't get into those. Essentially, we end up with this full target data set of 78,109 100-second average samples from MMS that we shown here have split into a training and validation data set comprising 80% of our total observations and a test data set composing 20% of those total observations. The features or the parameters that we are trying to reproduce using our algorithm were chosen to be the 3-component magnetic field vector, the 3-component velocity vector, and the electron density. So that's 7 components. All right, we have our targets here. So the inputs that we use, the wind data that we use, consists of time series data. So for each of these targets that I just showed you, they happen at a particular time. We assemble 100 minutes of wind data that ends 25 minutes before that target time. Notionally contained in these 60 measurements off of the wind spacecraft is all of the information necessary to predict what's going on in the solar wind at that place in time that we specified, the MMS's place in time. The features that are in our input data set, or the parameters that we give to our algorithm in order to predict what's happening at the Earth, are the 3-component velocity, the ion density, the ion temperature, the 3-component magnetic field vector, and the vector positions of both of those spacecraft in time. This way, we give the algorithm all of the information about the physical stuff that's passing by the L1 point, as well as the positions of the 2 spacecraft that we're trying to propagate between. Excellent. So now we get into the nitty-gritty of the algorithm. We'll step through it bit by bit. Unfortunately, this means ball and stick plots, but I'm going to try to break it down for the people who aren't used to staring at these. So there are essentially 2 parts of crime that are interesting, novel, motivated by the problem. The first of which is basically the first layer, the first step. We use a thing called a gated recurrent unit, which is a flavor of what's called a recurrent neural network, which is a neural network that has a sort of memory vector inside it of a certain size that it uses to store information. This is the kind of neural network that's in the thing in your phone that predicts the next word, right? So it steps through some sequence of information and assembles what are called relevant features. And then you can pass those features on to something that, in your phone, it assigns that to a word. So it has, probabilities of what word is next, and then your phone assigns it to a word. Here, what we do is we step through the wind input time series here with our gated recurrent unit, and then feed that information to a series of fully connected layers. These are sort of a vanilla neural network, the classical picture from the 70s. That does the propagation, and then the second part that actually has the secret spice, as it were, is the output layer. So rather than outputting scalar values for each of the 7 parameters that I talked about that are in our MMS data set, we output parameter distribution, so a mean and standard deviation defining a Gaussian probability distribution for each of those parameters at each of those target times. Through this, we are able to basically natively estimate the uncertainty in our predictions through the appropriate, an appropriate loss. Loss is another word for like goodness of fit almost, but by selecting an appropriate loss function, we can basically make these physically meaningful uncertainties on our outputs that are natively estimated by this model. I also have all of the nitty-gritty details in the bottom right. Happy to go through that, but that's for real nerds only. Real machine learning nerds only. We're all nerds here, right? Okay, I talked about this loss function. I want to go into it a little bit. Loss function, a goodness of fit metric, a scoring rule. Every field calls this a different thing, but frequently, when you have a prediction and an observation, how much your prediction matches your observation, if you want to quantify that, you end up with an equation that looks like this, right? Loss, score, whatever, equals the absolute value of your prediction minus your observation. It's shown graphically on the easy laugh. Sorry, I got an email. A prediction minus an observation. So for a deterministic prediction, if your prediction is just a scalar value, this is a natural, this is the absolute error, right? We all know this. The distance between these two numbers. For predictions that are probability distributions, i.e. have some kind of uncertainty, the picture looks like on the right. So instead of a single scalar value, we have a range of values that it can take. And certainly there are goodness of fit metrics that assess, how close this distribution is to this number that we're locking the shape of the distribution, right? You just say, oh, you just take the probability density right here. And that's your goodness of fit metric. And certainly you can do that. One difficulty with this is it doesn't take the form prediction minus observation. So that means that it's hard to compare the picture on the right to the picture on the left, right? If you have, some probability density, well, like, reasonably, how much more valuable, how much more accurate is this than that? It's hard to say. One way that you can make these things more comparable is by reformulating this picture and to end up with something that looks like prediction minus observation. So instead of the probability densities that I have plotted here, we'll instead shift to the cumulative distribution. So this is the same picture that I just showed, just in a different formulation. So the cumulative distribution for people for whom it's been a while since we've taken a stats class, is basically the probability that your value y assumes the observation value or below, or C of y, yeah. So basically, below y observation, it's 0, after y observation, it's 1, right? Similarly, you can define a predicted cumulative distribution by the probability that it's at your prediction or below. If you then subtract the two, and if you integrate the space in between these two cumulative distributions, you see you have this blue area right here. We call that the continuous rank probability score, or the CRPS. You can do the same thing for your Gaussian prediction. If you reformulate that Gaussian probability density function into a cumulative distribution, you end up with an error function. And you can also similarly integrate the area between these two curves in the blue right here. You can call that, that's also the CRPS. And this way, you can formulate it in terms of prediction minus observation. Instead of the absolute values of your prediction and observation, it's the cumulative distribution of your prediction and observation. And by comparing the blue area between these two curves for a deterministic and a probabilistic prediction, you have a sort of more comparable metric between the two. Cool. Let's talk about that in terms of the equations, if the graphics didn't make it. Yeah, we'll move to equations. So to say this in equation terms, the CRPS equals the integral over all possible values of your parameter of your predicted cumulative distribution minus your observed cumulative distribution. There we go, predicted minus observed. We've done it. Putting in the actual functions for these, for whatever prediction you have, you can define a cumulative distribution C of y. Say your observation is deterministic, then its cumulative distribution is just a Heaviside step function like we saw in those previous slides. Excellent. For a deterministic prediction, we know C of y, it's the Heaviside step function again. So what you can do is you can substitute, you can add in the Heaviside step function of y minus y predicted here, you can do out the math, and out falls the absolute error, our good friend. Excellent. So the CRPS, as we see, for a deterministic prediction, the CRPS is equivalent to the absolute error. For a deterministic prediction, say a Gaussian, we can substitute the error function in for C of y, and we get out this big equation down here, which might look gross on a PowerPoint slide, but is analytical and differentiable in sigma and mu, and therefore is usable as a loss function for our purposes. And indeed, it's also a formulation of the CRPS, so it's comparable to the absolute error. This function is, so this function, it can be used to train these Bayesian neural networks, which is finding an appropriate loss function for training a probabilistic neural network is a subject of debate and discussion and kind of difficult. You may have heard of another loss function called the negative log likelihood. This function is often better than the negative log likelihood for a couple reasons. One, it symmetrically punishes over and underconfident predictions. The negative log likelihood favors overconfident predictions, favors small sigma. This symmetrically favors over and underconfident predictions. Furthermore, again, as I said, it collapses or is equivalent to the mean absolute error for a deterministic prediction. Therefore, you can compare a deterministic and probabilistic model more readily. Also, this isn't as useful for computers, but it is highly useful for humans. It has the same unit as the variable of interest, unlike the negative log likelihood. So it's hard for a human to look at a negative log likelihood and say, is that good or is that bad? But if you have the CRPS, you can look at a function immediately and be like, a CRPS of 100 nanoteslas? That's very, very large, which is helpful, saves you time. And our time is very valuable. Excellent. So once we actually train this architecture, oh, you know what? I just said I just have prime on this slide and I forgot to say. So that architecture that I showed on that slide, we call it the probabilistic regressor for input to the magnetosphere estimation, or prime. I need to get my marketing better. So I actually introduced that earlier in the slides.
You have stickers?
Mhm.
You have stickers to give?
I wish I had stickers. That would actually be a really good idea. But either way, so once you actually train prime with this algorithm, or rather with this loss function, when you train the algorithm with this CRPS loss function, this is what its outputs look like. So these are two example outputs at two different times. If for one particular parameter, this is electron density. In the fast in orange on the left and slow solar wind in green on the right. The dashed lines are the observations off of MMS, and then the Gaussians are primes actually like predicted distributions. So what you can see here is this kind of is included both to give you an idea of, oh, prime doesn't just put error bars or confidence intervals, it's a full probability distribution, but also to give you sort of a sense of what we mean by this CRPS and ways that it behaves. So here for this, consider the fast solar wind here. MMS measures the density to be 1.99 per centimeter cubed. Prime outputs a distribution centered at 1.64 per centimeter cubed with a sigma width of 0.65 per centimeter cubed. This results in a CRPS 0.23 per centimeter cubed. For the slow solar wind, MMS measures, 8.29 per centimeter cubed. Prime outputs 8.50 per centimeter cubed. That's actually closer than this in terms of distance between the peak and the observation. But prime is a lot more uncertain in the slow solar wind. It has a wider sigma. And as such, the CRPS is higher. In the world of loss metrics, that's worse, right? A higher absolute error. So that can give you a sort of intuitive picture of how this operates. All right, the question hot on everyone's lips, is it better than Omni? Okay, so the way that we compared prime to existing algorithms is we used the same MVA planar propagation algorithm used to assemble Omni to propagate wind data to MMS rather than to the nose of the bow shock. This is to give it a fair comparison so that we're not having to, arbitrarily time shift data from the nose of the bow shock to MMS. On the top in green are joint distributions between primes outputs on the y-axis and MMS's targets on the x-axis for the 7 parameters that prime outputs plus dynamic pressure, because we want to know about dynamic pressure, and that's assembled from the density velocity. On the bottom in orange is our Omni proxy. This MVA shifted wind data for the 7 parameters plus dynamic pressure. I know that this probably is too, we'll zoom in on some of these so you can see in a little bit more detail, but what I wanted to say here is that for each of these components, both the CRPS is lower for prime in a statistical sense over our test data set than it is for the Omni proxy. So in a statistical sense, prime is more accurate than Omni. You can sort of see this in a little bit more detail with these joint distributions that I've zoomed in on here. On the top are density joint distributions, and on the bottom are dynamic pressure joint distributions. It overplotted is this dashed line to show where a perfect prediction would lie. We are not doing linear regression here. It's just to guide the eye. And what you can see here is that prime sort of lies evenly distributed on either side of this line. That means that its errors are random, whereas the Omni proxy here tends to overestimate density. And this results in a severe overestimation in dynamic pressure when you use that density to calculate dynamic pressure. As such, we are, almost 3 times more accurate than Omni at predicting dynamic pressure, which is one of the most important parameters used to determine energy transfer into the magnetosphere. So this is really great. That's the accuracy of prime. One of the other things that we said that we could do, that we can improve over existing algorithms, is our uncertainty. As such, it's important that we evaluate the reliability of prime's outputs. This was something that was new to us when we started this analysis, and I think a lot of people in this room are interested in uncertainty quantification on models, and especially on probabilistic models. So I thought I'd dig into this at least a little bit. A probabilistic forecast is considered to be reliable or well calibrated if the probabilities that it predicts of events are matched by the observed frequencies of those events. For instance, if you had a weather model that told you there's a 70% chance of rain tomorrow, you better hope that 70% of the time it will rain tomorrow, right? Since prime's outputs are Gaussian, this is actually, you can actually calculate this directly. For weather models, you frequently have to be bin this, but you can actually calculate this directly. So on the x-axis here is the predicted frequency of a given parameter attaining a particular value on the x-axis, and the observed frequency of a particular parameter obtaining a particular value on the y-axis. A perfectly reliable model would be a straight line. Any deviations from that indicate that there is some deviation from perfect reliability. That's the dashed line, is the perfectly reliable line. And we've sort of reformulated this into over and underestimation of a given probability here. So what you can see is prime tends to overestimate the likelihood of overestimate the likelihood of unlikely events and underestimate the likelihood of rather likely events by within, roughly 10%, which is actually pretty reliable relative to other probabilistic space weather models whose probabilities have been, the calibration of the probabilities have been determined. So that's good, and it's also slightly conservative, which in the world of models is a good thing, because it means that your extreme events are more likely to be caught. Excellent. What does it look like with regard to real data? So here we have comparison to real data from MMS1. This is during a co-rotating interaction region. So that's when a fast solar wind flow overtakes a slow solar wind flow, runs into it, and forms a shock. this is an algorithm that is very hard for planar propagation algorithms to accurately propagate because it predicts that the fast flow will pass through the slow flow unmodified. What we can see here is that, so in the dots are the ground truth from MMS. The crosses are, again, that sort of omniproxy, the minimum variance shifted wind data. And then the dashed line with the shaded region is Prime's predictions with its 1 sigma uncertainty bound. What you can see here is that indeed this MVA algorithm gets the arrival time wrong by almost 30 minutes. What you can also see here are some indications of how Prime actually operates in the real world. So what you can see is that Prime gets the arrival time more accurately than I would say the MVA algorithm does, but it is a little bit slow to react. This is a known consequence of neural networks. It's something that there's a lot of thought being put into how to overcome right now, and it's something that we're looking to address in future versions of Prime. You can also see that, as expected, the uncertainty downstream of this shock, i.e. the right side of this plot, gets much larger. You know, shocks are these stochastic processes where all of this hard to predict physics happens. And indeed, Prime says it's harder to predict this value downstream of the shock. So that's great. One other sort of room for improvement thing that I want to point out is that, as you can see, so this is the x component of the velocity. Indeed, downstream of the shock, the uncertainty gets much larger, but it gets larger symmetrically. And that's because Prime's outputs are necessarily Gaussian. What you kind of want your model to do in an ideal world is when it sees this sharp jump negative in the parameter, you'd want its uncertainty to extend in the negative direction more than the positive direction. Unfortunately, that's not something that our model can do. So in order to capture the behavior of this jump right here, it extends in both directions simultaneously, which of course decreases its reliability. So something we're looking to address with more flexible output distributions. Here's some more example data. Oh, I should note that CIR was from our test data set, so the model hadn't seen any of that data. And this is more data that it hadn't seen. So this is data from 2022. This is a ICME. This is one of the ICMEs that was thought to provide the necessary preconditioning for that Starlink launch failure in February of last year. And what you can see is similarly to the last event, Prime gets the arrival time of this event more accurately than Omni does, or the Omni proxy rather. One issue that the Omni proxy has during this event is that it starts mixing plasma. So the way that the propagation algorithm for the way that the Omni team handles these out of sequence arrivals is they propagate all of the solar wind as is and then rebin it to a new time series. So you can see that this plasma starts jumping around, these conditions start jumping around close to the interface in this sheath region rather. And that's because it's averaging two different plasmas. Prime doesn't do that. But you can see it still has this sort of like slow change process, problem. And indeed, also another problem is that it gets sort of confused about magnetic field in the middle here. This is another thing that we're working on in future iterations of Prime, is that the classification algorithm that we use removes all shocked plasma or anything that it determines looks too much like the magnetosheet. And indeed, during this event, even though this wasn't part of our training data set, plasma that looks like this would have been removed. And indeed, when we apply our classifier to this, it determines that this is the magnetosheet. It isn't actually the magnetosheet, it's a different kind of sheet. But indeed, they look similar enough for our classification algorithm to remove that. So adding back in ICME sheets is something that we want to do in future iterations of Prime.
Sorry,
Yes.
Mr. Fink, so is this semi has been removed from the data or not?
So had this event been in our data set,
Oh,
it would have been removed.
yes, okay.
Yes. So similar events like this, similar ICMEs
Yeah,
have had their sheets removed by our classifier.
just the sheet.
In adjournment. Just the sheet, yeah. Anything that looks too much like the magnetosheet. Also, anything that looks too much like the
Like,
Photoshop.
don't you take like some margin after after the.
Before and after, yeah, so
Yeah, so-
basically we need to be stable in the same region within, it's 4.5 times, why am I, sorry, 450 seconds. I could multiply 4.5 by 100 because it's
So,
in front of
so
me.
you basically just remove the rest of the CME then, so you have the
Yes.
magnetic ejector.
Yeah, but adding those back in is something that we wanna do to our training set, excellent. So, sort of talking through some preliminary applications that we're working through right now. Up until very recently, I was working on the manuscript for all of this, so I haven't had time for applications as much, but I want to point towards some things that we're excited about, because we also welcome collaboration. So this might get you thinking, and then you can talk to me about an idea, and I'm happy to work on stuff with this, because God knows I've looked at enough Keras code. I want to look at data. So there's this idea of, so talking about polar cap potential saturation, just to introduce this problem here. This has kind of gotten some attention in our field recently. Basically, the driving solar wind. Oh, yeah, sorry.
No, 5 minutes left. roughly.
5 minutes? Awesome. We're speeding towards the end. So the solar wind has this motional electric field that it applies at the day-side magnetosphere. This electric field maps down field lines into the polar ionosphere, and you can measure it as a potential there. So we're calling the driving solar wind field EM here, and then the polar cap potential EPC. People have noticed that for small values of the solar wind electric field, the polar cap potential is roughly equal to that. For large values of the solar wind electric field, the polar cap potential does not follow. It tends to saturate. That's what people observe. However, many conflicting measurements of the exact value at which EM no longer gets applied down into the ionosphere have been made. So people disagree on where this saturation actually occurs. And there've been, depending on who you ask, almost a dozen different measurements of this value of saturation. And almost as many physical models have been proposed as to why this occurs. Some people have argued recently that the saturation I'm talking about, so yeah, here is the that effect in graph form. So here's the solar wind electric field, and then this is the polar cap potential that's measured, and you can see that, yeah, for small values of the EM, it's roughly linear, and then you start to saturate at some value. Some folks have argued that if you have some uncertainty on your EM input, that uncertainty, if EM and EPC actually have a truly linear relationship, if you have uncertainty on your value of EM that you measure, that shows up in the data as a statistical saturation. Indeed, this is also called regression to the mean, and is indeed where the term regression even comes from for regression analysis. These researchers also showed that if you assume some uncertainty, they just picked some reasonable sounding values for this analysis here. If you just pick some uncertainty, you can actually reproduce this effect exactly from a linear relationship. And if you subtract that out, you can actually recalibrate data by assuming some uncertainty. So one thing that we're in the process of doing is use prime's outputs to actually directly calculate this uncertainty rather than assuming some uncertainty, and thereby actually putting a confidence interval on this is the value that we expect saturation to actually occur at, and thereby reject some physical models. So that's one potential application. Another potential application that we're really excited about is basically ensemble modeling. So we've taken prime's outputs and used them to drive the space weather modeling framework global MHD simulation. So here are some results from that. So on the top is the polar cap potential measured from SWMF when Omni is used to drive it. So in blue is the Omni-driven SWMF, and then gray, even though it's labeled Omni here, this is the measured polar cap potential. So this is ground truth reality here. In gray, and then on the bottom is the same time frame, but instead we use prime to drive SWMF. this is sort of all of the computation time that we've had with our collaborators here. So right now, to me, it's unclear whether one is better than the other. You can see here, like the peak, I think that prime tracks that a little better than, or rather using prime to drive SWMF reproduces this peak better than for Omni, but there's other times where it's not as good. So one thing that we want to do is do this a bunch of different times with perturbed inputs from prime. So using those uncertainties to basically evenly sample throughout a Gaussian and thereby put some error bars on these global MHD simulations. So if you have any spare computation time lying around, I'm interested in pushing that up. Yes, so I've got a minute left. We can do conclusions. So a record of solar wind at the Earth requires a propagation algorithm, full stop, because we don't have a continuous monitor upstream of the Earth right now. The most popular versions of these algorithms, have notable limitations. Our new algorithm, the probabilistic input to the magnetosphere estimation algorithm, is more accurate than these traditional algorithms. And it also attaches physically meaningful uncertainties to its predictions. This algorithm has potential applications to things like ensemble MHD modeling, investigating problems thought to be uncertainty limited, and really any study that utilizes Omni data. So we are open to collaboration. We have some data that's hosted, and we're working on making this more accessible, not acceptable. Both, I suppose, right? So let us know if you want to take a look at this stuff. And yeah, I'll just leave this up here, and feel free to scan that QR code to go to our GitHub for an implementation of Prime and some CDF data.
Any questions in the audience? Don't be shy. Yeah, sure.
In your algorithm, do you have any physical constraints?
We don't have any physical constraints. Well, so we don't introduce any physical constraints in our loss function. We do have some amount of physical assumptions that have snuck in. For instance, by choosing a particular input window, we have put the physical constraint that all of the information that the model needs is in this particular time frame, which we determined that input time series via hyperparameter search. So that's the optimal length to use. But there still could be situations in which that limits us.
So you don't verify if you conserve energy or stuff like that?
We don't verify that we conserve energy, no. Nor do we verify that we conserve things like particle flux, because it's hard to determine a boundary over which to determine that. So one thing that we are working on right now is a magnetosheet model, which is, we're getting through validation right now. And that, since we have solar wind on one side and then shock plasma on the other, we can determine that. Yeah, I should have put that in. I finished doing that exact analysis like right before getting on the train. So I should have put in some extra slides. I had some time today. But yeah, so we didn't verify that for the solar wind version of Prime, but for our cool magnetosheet model, we are doing that.
I had a comment on the comparison you were doing with the Omni versus ground truth for the polar cap. A couple of slides back.
This guy?
One, yeah.
Yeah.
What it looked to me is like is that with the Omni driven data, that there appears to be maybe my eyes are fooling me, but it looks like there's more of a systematic bias in favor of overestimating the polar cap potential, where in Prime it's more symmetric. There are times when you got it too high and there are times when you got it too low.
Yeah, I think that I agree with that, especially like, here to here, here to here. That points to why like I want to do some ensemble modeling, because it could be that if you expand that balance, it's all within that error bar.
But the Omni driven actually gets better like at the end.
Yeah,
Like
the
actually
declining
like
phase, it gets much better.
yeah, you're biased toward the value. While the Omni actually have like a better estimation.
Yeah, that's true. Which it could be that if you sort of symmetrically perturb something like, Vx, it might not actually have a symmetric biasing effect in the polar cap, right? So, but yeah, whether one is better than the other a priori, I have difficulty determining. So,
Right, that part is not obvious, which one has the lower loss function.
right. Yeah.
Show again the slide with the CME and the SIR, please.
Yeah, do you prefer the ICMU, the
If you could like swap between the two. So it seems like, for instance, for the speed, like for the SLR, like your error bars like goes crazy.
Yeah,
And that for the CME, is it something that you observe for most, like for all the CMEs? Or is it like for like all the CMEs that you have in a data set? Do you feel like, do you see that actually the prediction is better, or like you have less error bars for CMEs than for SIR?
well, so it depends on the jump. So the problem with the difficulty with this.
Because you also have a jump in the
is
CME
wrong.
because you have
That is just. Huh. Weird.
because the jump is higher for the CME, that's what I was already.
No, never mind, this is wrong.
Okay.
Yeah, I'm not sure about that, actually. The, error bars that are, determined here are through. Yeah, actually, I don't have a good answer for that. I thought I did, but it turns out that I was mistaken on the scale of the jump for this CIR off the top of my head. Yeah.
Okay.
I don't know if the error bars are systematically smaller or larger during.
Because I
CMEs or not.
I would expect like for a CME, that is impact like the inner part of the CME, that would be easier for a code because you have a higher magnetic field, you cross like a structure, coherent magnetic structure.
Right.
You are on the SAR, you have the interaction of like two different populations slowing.
Yeah,
So it's more, you have more physics going on.
there is
then-
more physics going on here.
And then
that's
that would
true,
be more
that's true.
difficult for your algorithm to predict what's going on.
Right, where on the right it's
yeah.
shock plasma, whereas here
Yeah, or just-
you might see some rotation that looks a lot like this
Yes.
at L1 versus here. That's actually a really good point. That could be why we're seeing this large jump in uncertainty. To my memory, this jump was much larger, and that was my explanation, but this jump is not as large.
Right, you have different scales on the graphs, and that's something that will trip you up if you're not careful.
Yeah.
Is there any question online? I don't think so. Someone says we love trains.
Mike.
Okay.
What?
Someone says we love trains.
think.
Oh, yeah, well, back when I was talking about.
Okay.
That was a long time ago, yeah.
Okay, so it was like a while ago, okay.
It was a while ago.
Are there any other questions? Perfect, so let's thank our speaker again.